Hello everyone. So in this video we will see the analysis of symmetric and asymmetric square waves. So this will be used in further RC circuits concepts. So that's why I am doing it here. So any periodic signal, xt is what? Periodic. So any periodic signal, any time domain periodic signal can be replaced with a DC voltage and orthogonal sinusoids and cosinusoids. Okay, an cos n omega naught t plus bn sin n omega naught t. So this is the DC and these are frequency content. So it will have omega naught 2, omega naught 3, omega naught 5, 5 omega naught by depending on the value of n1. So any signal can be broken into this form. Okay. So now over in this question our DC value is this is t, right? This is 2t and here this is minus t. Okay, so our DC value is here, our a naught is 0, right? You can see, and our xt is odd function, right? If it is odd function, then your an will be 0. Only bn exists. Okay. If it was even function, then only an would exist and bn would be 0. Okay. And for the calculation of bn is 2 by t 0 to t xt cos n omega naught t dt. Okay. So bn would be 2 by t 0 to 2t by 2. For 0 to t by 2 it had a value cos n omega naught t dt minus t by 2 to t a cos n omega naught dt. Now you can simply solve this. 2a by t 2a by t sin n omega naught t upon n omega naught. So there is one mistake, I guess. I am writing cos here, it would be sine. So let me improve it. So it would be from 0 to t by 2 minus cos n omega naught t upon n omega from t by 2 to t. Okay. So here minus 2a by n omega naught t. So here we will have n omega naught t by 2 minus cos 0 is 1 minus cos n omega naught t plus cos n omega naught t by 2. Okay. Omega naught equals to 2 pi by t, right? So omega naught t is 2 pi. So by solving this we get, I have solved it here. Your bn will be 2a by n pi 1 minus 1 to the power n. Okay. Your an is already 0 and your a naught is also 0. So for n equals to 1, your bn is, for n equals to 1 it would be 4a by pi, right? For n equals to 3 it would be 4a by 3 pi. For n equals to 2 your bn would be, for n equals to 2 it would be 0. For n equals to 4 it would be 0. So your bn can be written like something like this. 4a by n pi. Your Bn is 4a by n pi, where n is 1, 3, 5, like this. So what does that mean? Here only chord harmonics exist. Okay, so your xt can be written in this form: 4a by pi sine, right? 4a by pi sine omega naught t plus 4a by 3 pi sine 3 omega naught t plus 4a by 5 pi sine 5 omega naught t, and so on. So here we have f naught, 3 f naught, 5 f naught, 7 f naught, all these components. Okay, and 2 f naught, 4 f naught, 6 f naught, all these components doesn't exist, only these components exist. Now let's take yt equals to xt plus a. Okay, this is the symmetric square wave we are having. Now we are shifting it up by a. Okay, we are shifting it up by a magnitude. So what will be the new waveform yt? So your yt will be so okay, so your yt will look something like this: 2a 0 2a 0. Okay, so the signal is shifted upwards. Okay, so what was your xt? Your yt is xt plus a, right? Xt plus a. So your yt can be written something like this: a plus, what was xt? Xt was this, right? Let us call it equation 1. So this was xt, so you can simply write it here: a plus 4a by pi sine omega naught t, 4a by 3 pi sine 3 omega naught t, and so on. Okay, so this is your yt. So what is the difference between yt and xt? Frequency components are same, right? Frequency components are same. Only DC value is added. Only average value or DC value is added. This is the average value. What is the average value of the signal? Average 2a into t by 2 upon t, that is equals to a. So only average is added. The frequency component is same, right? The frequency component doesn't change, be it symmetric square wave or asymmetric square wave. The frequency component remains the same. So what is the conclusion? So conclusion is, for any square wave, for any square wave xt. Okay, so xt equals to average plus what should we write? Average plus sinusoid or cosinusoid frequency component of amplitude to v by n pi, where v peak to peak value, and n is 1, 3, 5, 7 and so on. Okay, so we have only zero frequency component, means DC, that is DC, and then we will have F naught, 3 F naught, 5 F naught, 7 F naught and so on. That means we have odd harmonics. Okay, so that's the way we should write it. Do you get it? Okay, so any square wave can be broken into these kind of components. Okay, so it will be broken into DC plus odd harmonics. Okay, 3 F naught, 5 F naught, F naught, 3 F naught, 5 F naught, 7 F naught. Not a single even harmonics, only the odd harmonics we will have. We will have only odd harmonics, we won't have any even harmonics. The amplitude you can remember, it is 2 into peak to peak value upon n pi. What is the peak to peak value here? 2a 0. So peak to peak value is 2a. So what is the amplitude? 2 into peak to peak value, 2 into 2a, so 4a by pi. Okay, and here what is the amplitude? In this one, what is the peak to peak value? It is 2a only. So here also we have 4a by n pi magnitude. Okay, so whatever the peak to peak value is. Okay, so we will see the analysis of RC circuit with pulse input now. Okay, thank you. Hello everyone. So in this question we have to analyze this RC circuit for these two conditions. T is very greater than RC and T is very less than RC. Okay. So we will tell the output waveform, then we will tell the value of output at steady state. Okay. Then we will tell output current at steady state. Okay. So all these things we will do. So let us draw the output waveform first. So what is the first condition? What is the we will draw the output waveform for first condition now. So T is very greater than RC. So this is what? This is time constant. Time constant of circuit. Tau is lesser than what? Lesser than the input waveform time period. Right? So we will have enough time for charging and discharging. What does that mean? That means that there will be complete charging and discharging. Why so? Because this time is very large. This T is very large, very larger than RC, and it would take 5 RC time for complete charging and 5 RC time for complete discharging. 5 to time it takes, right? You know that. So it will take 5 RC time for complete charging. So there will be enough time for charging and there will be enough time for discharging. So for 0 to T by 2, our V in is 10. So this is our circuit. RC. This is V naught and here we have 10 volt. Okay. So your output will go something like this. You will have enough time for charging, right? So it is from 0 to T by 2, it is 10 volt. Okay. Now at T equals to T by 2 plus, what is the circuit? At T equals to T by 2 plus, V in is 0, right? At T equals to T by 2 plus, V in is 0. So this V in is 0. So this R will be connected to ground and this V output equals to VC equals to 10 volt. So this C is 10 volt. Okay. Now what happens is that this capacitor discharges. So capacitor discharges through resistor. Okay. So now there will be discharging. Okay. This is V naught and T. So let us assume this is T by 2 from T by 2 to T. Okay, so now the capacitor discharges. So now again for T to 3T by 2, capacitor charges. For 3T by 2 to 2T, capacitor discharges, and the same cycle goes on. Goes on. There will be complete charging and discharging. Okay, you get it? How will be the waveform of V naught? V naught T. Okay, this is 0 to T by 2, T, 3T by 2, and 2T, and the same cycle goes on. Okay, this is 10 volt. Okay, so I hope you have understood this. And talking about the current waveform, if we want to draw the current waveform, I naught T. I naught T. So what is the I naught T in this question? The I naught T will be this value. Okay, I naught T. So initially the current at T equals to 0, the current is 10 by R, and slowly the current decreases. Okay, look here, if you talk about the current I naught at T equals to 0, it is 10 by R, and then when the capacitor is charged to 10 volt, it reduces to 0. So from 10 to equals to 0. Here it is 10 by R, then it goes to 0 till T by 2. Okay, and in this one, if you talk about I naught, I naught, so it is in, this is I naught, right? This is I naught, but the current is in opposite direction. So it is minus 10 by R, right? And slowly the complete capacitor gets discharged. So this will be the waveform, but I shouldn't draw it from here. I should draw it from here. So it's completely gets discharged. So this is time T, and this is T by 2. Okay. So it starts from minus 10 by R and it discharges completely. So it will go something like this. Okay, 10 by R and minus 10 by R. Okay, and this is time T. And this will be T by 2, T, and 3T by 2 and 2T. Okay, so I hope you have understood this concept. Now we will see one more method for that. Okay, method 2. So for method 2, this was the input waveform, right? And this input waveform is what? Square wave, right? This is square wave. And what are the frequency component a square wave has? Frequency component. Frequency component. It will have a DC, F naught, 3F naught, 5F naught, 7f0 and so on. So all these frequency component this waveform will have. Okay, and now we have a RC circuit, right? This is a RC circuit. This is what? A low pass filter, right? This is a low pass filter. V0 s upon V in s is 1 upon RCS plus 1, right? So this is a low pass filter with cutoff frequency. Cutoff frequency is 1 by RC, right? So this is how the waveform looks like. This is what V0 s by V in s, and this is the frequency, right? This is how the waveform will go. This is the frequency response of RC low pass filter, and this is 3 dB cutoff frequency, that is 1 by RC, and here we have gain 1. So only at 0 frequency we have no distortion. After that we will have some distortion, right? Now what is given? Look, wait. So first point is that this is a filter, okay, and you are giving your input waveform that has 0 frequency component, f0 frequency component, 3f0 frequency component, and 5f0 frequency component. This is your input, and you will have some output, right? This is the condition, right? Okay, so what is given is that given T is very greater than RC, that is given. Okay, so now f will be very lesser than 1 by RC, right? So all the component DC, f0, 3f0, 5f0, this is input, right? This is input, and this is RC circuit. This RC is from RC circuit, and this is the input time period. So the input frequency is very less than RC. So all these component DC, f0, 3f0 will be lesser than 1 by RC, right? Like with time the value is increasing. Okay, it can go near to RC, but it will be lesser. Okay, so what happens is that almost all the frequency components, like almost all the frequency component are lying in this region. Okay, all the frequency component, almost all the frequency component are passed with minimum attenuation. What did you see here? You saw that you are having a low pass RC low pass filter with cutoff frequency 1 by RC, and the input waveform has some frequency component 0, f0, 3 f0, 5 f0, 7 f0, but all the frequency components are lesser than 1 by RC. So all the frequency components are being passed with minimum attenuation. Okay, there will be attenuation. Here you have gain 1. The DC will be passed. This will be passed completely. This will be passed completely because this is 0 frequency, and at 0 frequency we have DC value. This is DC. So DC will be passed completely, but all other frequency component will have attenuation, but very less attenuation. From here we will have more attenuation, but here there will be very less attenuation. So all the frequency component are passed with minimum attenuation. So the output will nearly follow input. Do you get it? If all the frequency components are getting passed, like we broke the xt yt, or you call yt, we broke the yt in this component, in these components. If this is getting passed, this is getting passed, almost all are getting passed with same attenuation, with same amplitude, then if you redraw it, it will go something like this only. right? If you combine all these sinusoid components, 4a by pi, 4a by 3 pi, if you combine all these sinusoid components, you will get the square waveform again. So output will nearly follow the input. Okay, since all the frequency components are getting passed, it will again have 0 f naught, 3 f naught with nearly same amplitude, nearly same amplitude. Okay, with nearly same amplitude it will be having these frequency components. Okay, so output will nearly follow input. So talking about the waveform now, this was your input. Let me. So in the waveform, this was your V in, and your V naught was something like this, right? It was getting charged and then discharge, charge and then discharge. So it is going like this only. Okay, so it is nearly following the input. This is what V naught, nearly following the input. Do you get my point now? Okay. Since all the frequency components are getting passed with minimum attenuation, the output will nearly follow the input. So it is going like this. Okay. So if the interviewer asks you to analyze a circuit with respect to RC low pass filter, then you will analyze the circuit in this way. Okay. And what did we see? We saw that the DC component is passed without any attenuation. Any attenuation. So your average value of output will be average value of input, and that is equals to 5 volt. Like if you don't understand it, 10 for t by 2 time and 0 for rest of the time, and then time period t. So it would be 5 volt. You get it? The DC component, DC component is at 0 frequency. This is getting passed with 1 gain. So it is getting passed with 0 attenuation. No attenuation. There is no attenuation. Okay. So it is getting passed with 1 gain. So the DC component is passed with 0 attenuation. So the output, so average value of output will be average value of input. And at steady state, at steady state, the average capacitor current is 0. You won't say at steady state capacitor will be open circuited. No, you won't say that. At steady state, average capacitor current will be 0. Why so? There will be no charging or and discharging. The steady state is reached when there is no charging or discharging. That means the average capacitor current is 0. So if IC average is 0, what you can do? This IC average is 0. So you will replace it with open circuited. This is your V naught and this is your V in. Then your IR average will also be 0. If your IR average is 0, then your VR average will also be 0, right? Because your VR average will be IR average into V, IR average into R. So it will also be 0. And your V naught average will be equals to V in average. That is equals to 5 volt. So I hope you have understood this concept. Okay, so now we will see the second condition. Okay, thank you. Hello everyone. So now we will talk about the second condition, that is T is very less than RC. Okay, so here this is the time constant. So here time constant, this is time constant tau. Tau is larger than what? Larger than input time period. That means incomplete charging and discharging. Incomplete charging and discharging. Okay. Here the time constant is very high. So to reach the steady state, what is the time you require? 5 to. It means you will require 5 RC time. So the time constant is very high. You need a lot of time to reach the steady state. But the time you have, like T by 2 is very less than RC. So there will be not complete charging and not complete discharging. Okay. So for 0 to T by 2, 0 to T by 2, here we have 10 volt R and C. R and C. Here we have 10 volt and this is your V naught. The capacitor charges. Capacitor charges. Okay. At t equals to 0 plus, what is the current? I equals to 10 by R ampere, right? We can call it the speed of charging, right? Because speed of charging. Because this 10 by R current will charge the capacitor only, right? This 10 by R current will charge the capacitor. Then slowly there will be some charge developed across the capacitor. Then the further, if the charge is developed, then the further current will charge the capacitor. So at t equals to 0 plus, this is the speed of charging, right? So now the capacitor charges. Since RC is very greater than t by 2, capacitor doesn't charge completely. Let's assume it charges to 3 volt. Okay, let's assume it charges to 3 volt. So your V naught will go something like this. It has charged to 3 volt only. 402 T by 2. Okay. Now at T by 2 plus, at T equals to T by 2 plus, your V in is 0. So circuit will look something like this. This is R. This capacitor is having 3 volt now. This capacitor is having 3 volt now. And if we are calling this as I, okay, so now the speed of discharging speed, that will be minus I, right? Minus I, because we were calling I in this direction and now the discharging is happening in this direction. So your minus I will be 3 by R, right? Now the capacitor discharges, but lesser than the value of charge gain. Okay. Now the capacitor will discharge, but the speed of discharging is here 3 by R, and here the speed of charging was 10 by R initially. Initially the speed of charging was 10 by R, and here the speed of discharging is 3 by R. So if it is getting 3 volt charge, so if it is getting 3C charge, like here it got 3 volt. So the charge that it has got is 3C, Q equals to CV. So it has got 3C charge, right? If it has got 3C charge, then it can't discharge for 3 volt. Okay, it has got 3 volt in initially, so it can't discharge for 3 volt because the speed of charging is less. So if we are going from 0 to 3, it can't come down from 3 to 0. It will come down to 3 to 2 or 3 to 1 to some value, but it can't come down to 0. Why so? Because the speed of discharging is 3 by R here, and here the speed of charging was 10 by R, so it was more. So the voltage gain will be more. Okay, and if this is less, then the voltage that we the voltage that we lose will be lesser. Okay, so now if you talk about V naught, we are going from 0 to 3. Okay, 0 to 3 volt. From 0 to 2 by 2, we went from 0 to 3 volt. Now we will come down, but not completely. Let us assume it discharges to 2 volt. Okay, let's assume it discharges to 2 volt, not completely. So it has discharges to 2 volt now. Now what you see, at t equals to t plus r c, this is r, this is c, this is 2 volt and this is 10 volt here. Now the speed of charging is at t equals to t plus, it would be 8 by r, right? The speed of charging is 8 by r. In first cycle we gain 3 volt. In first cycle we have gained 3 volt with speed of charging 10 by r. Now the speed of charging is 8 by r, so we can't gain 3 volt. We will gain lesser than 3 volt. The capacitor charges but lesser than first cycle. Do you get it? Now if we draw the output waveform, we know t, it will go something like this. From 0 to 3 you went, then 3 volt to 2 volt you came. So in first cycle we have a gain of 3 volt. Now we can't have a gain of 3 volt. We can have a gain of lesser than 3 volt. Let us assume we have a gain of 2 volt. So it will go to 4 volt. Right? It will surely go above 3 volt, but it will surely go above 3 volt, but it will go lesser. It will gain less. Okay, it has gained 3 volt here. It will gain, and here on it has gained 2 volt. Here it has gained 3 volt, right? But here it has gained only 2 volt. Okay, so now we have reached to, now this is the condition, this is time t and this is 3t by 2. So here we have gained 4 volt. Here we have gained 2 volt and we have reached to 4 volt now. Okay, now at t equals to 3t by 2 plus, at t equals to 3t by 2 plus, your Vin is 0, Vin is 0 volt. So this is R. Now your Vc is at 4 volt, right? Your Vc is at 4 volt, or you can call it C. Now the discharging speed is, that is minus I, that is 4 by R, which is more than previous cycle, right? In previous cycle, what was the discharging speed? In previous cycle it was 3 by R, right? Now it is 4 by R. So now the capacitor discharges and discharges more. In previous cycle it discharges for 1 volt. Now it will discharge for more. It will discharge for 1.5 volt. Okay. So now drawing the waveform. First till 3, then it went to 2, then it went to 4. Now from 4 it will come to 2.5. Okay. Here I will write 3 volt, 2 volt, 4 volt and 4 to 2.5 volt. Here we had a loss of 1.5 volt and here we had a loss of 1 volt, because here the speed of charging is increased, so we will have a more loss, right? and here we had a lesser loss. So this is V naught T and this is T. So let me draw it more clearly. So this is your output waveform, right? So the same cycle goes on. Same cycle goes on, right? So here we had at t equals to 0 plus we had 10 by r speed of charging, right? Here we had 3 by r speed of discharging. Here we had 8 by r speed of charging. Here we had 4 by r speed of discharging. Here we had 7.5 by r rate of charging. This was charging. This was charging. This was discharging. This was charging. This was discharging. This was charging. Okay. So we had charging, discharging, charging, discharging, and charging. So what do you see here? The speed of charging is getting reduced. 10 by r, 8 by r, 7.5 by r. But the speed of discharging is getting increased. 3 by r, 4 by r, and further increases. Do you get it? So here speed of charging is getting reduced, but the speed of discharging is getting increased. Okay, the speed of charging getting reduced from 10 by r to 8 by r and so on. 10 by r to 8 by r to 7.5 by r and so on. Speed of charging is getting increased, so 3 by r, 4 by r and so on. Speed of discharging is getting increased, so 3 by r, 4 by r and so on. So when we will have the steady state? At steady state, when we will have steady state, no further charging, no further discharging. At what time? When speed of charging is equal to speed of discharging. If speed of charging is more, then the capacitor will charge. If speed of discharging is more, then the capacitor will discharge more. So at steady state, speed of charging should be equals to speed of discharging. Okay, so at steady state, both should be equal. So that means, what does that mean? V naught equals to how much value? Vi by 2. That means equals to 5 volt. So at that time, the speed of charging would have been 5 by r and speed of discharging would have been also 5 by r. This would be charging and this would be discharging. So both of them will be equal. Okay. So your output, this is how your output will look like. Steady state output. This is V naught T. There will be some ripple, right? Because we are talking about this one as it at edge. Okay, we so all the current at edge only. 10 by r it was at edge only, 3 by r then it reduces, right? Then 8 by r it reduces. So but we are talking about edge only, so this ripple will also be there, but the average value will be 5 volt. Okay, so the ripple will be there, but this average value will be 5 volt. Okay, this value will be 5 volt. This is some we can call it mt by 2. We can call it m plus 1. No, not m plus 1. This would be mt. This would be m plus 1 t by 2 and so on. Okay, but the average value will be 5 volt. So the steady state value of output, steady state average value of output will be 5 volt only. I hope you have understood the concept now. Okay, so now this is your circuit at steady state. This is at steady state. So at steady state, this is R, C. This is at 5 volt fixed. Okay, this is V naught. and this is the current IR or IC, whatever you can say, and this is here you have V in. So here we have 10 volt, 0 volt, 10 volt, 0 volt, 10 volt, 0 volt, 10 volt, and 0 volt. Okay, so your at steady state, this 5 volt is fixed. So what will be the value of IR? Let us call this one as MT, this one as M plus 1 T by 2, and so on. Okay, so for MT2 M plus 1 T by 2, your V in is 10 and your V output is 5 volt. This is 5 volt and this is 10 volt here. This is R, this is C, and this is P naught. So what is the current? Current I equals to IR equals to IC, that is 5 by R. Okay, and now for M plus 1 T by 2 to M plus 1 T, your V in will be 0 volt, right? Your V in will be 0 volt here. Your V out will be 5 volt. So what will be the current? I equals to IR equals to IC would be minus 5 by R. Okay. So at steady state, what is your current waveform? Current waveform at steady state. So at steady state, what is the current waveform? First it is 5 by R, then minus 5 by R, okay. This is T, this is I naught or IRT or whatever you can say. This is 5 by R minus 5 by R. Okay, this is time T. So IR average at steady state, it would be 5R into T by 2 plus minus 5R into T by 2 upon T. So it would be 0 ampere. So your steady state average current is 0 ampere. So your VR average at steady state, it would be IR average into resistor, so it would be 0 volt. Okay, so what do we see here? The average steady state current is 0 ampere. The average steady state voltage across resistor is 0 volt. So the average steady state voltage across the capacitor is 5 volt. Okay, so these are the four answers. Now we will see method 2 and method 3 for that. Okay, so it will be a very interesting discussion. Okay, so let's see the method 2. So in method 2, R, C, and this is V naught, and here we have V in. So what do you say? At steady state, there should be no charging and discharging in capacitor, right? There should be no charging and discharging in capacitor. So the average capacitor current should be 0. The average current flowing through the capacitor should be 0. You won't say the capacitor will be open circuited. You won't say that. You will say the average capacitor current should be 0 at steady state. Why so? Because there should be no charging and there should be no discharging. That's why the average capacitor current should be 0. So we can make the circuit like this. The average current is 0. Okay, and this is V in. So if this is 0, then your IR average will also be 0. right? This is 0 ampere, this is 0 ampere. Then your VR average at steady state will also be 0, not 0 ampere, 0 volt. Okay, and your V naught average will be same as V in average. Why so? Because there is no voltage drop, so it would be same as V in average, and that is equals to 10 into T by 2 plus 0 upon T, and that is equals to 5 volt. So do you understand it? Initially, sorry, at steady state, the average capacitor current should be 0. So your I average should be 0, and your VR average should be 0, and your V naught average should be equals to V in average, that is equals to 5 volt. So in any configuration, if they ask you, if they have given some pulse input, the duty cycle may be 30%, their duty cycle may be 40%, 70%, any input. If they have given any input, the duty cycle is, let us assume we have 30% duty cycle. Okay, the peak value of input is 10 volt. We have 30% duty cycle, and they have asked the output voltage of capacitor at steady state. Average output voltage of capacitor at steady state. So what will be the answer? Answer will be 3 volt. Why so? The average value of output will be same as the average value of input, right? The average value of output will be same as the average value of input at steady state. What is the average value of input? Duty cycle is 30%, so 10 into 0.3 by 1, so it would be 3 volt. So output voltage will be 3 volt. We will see more circuit like that. So that's how you can analyze it. Okay, so now we will see method third. That's a very interesting one. Method third. Okay, so method third, again the circuit that we had, this was the circuit we had, RC. This is V node and this is V in. This is what? RC low pass filter. RC low pass filter. So your V naught S upon V in S is 1 upon SRC plus 1, right? So again, I hope you are liking the discussion here. This is completely different from what we study in books or anything. Okay, so if you go by these analyses, then interviewer will be very much impressed. The cutoff frequency is 3 dB cutoff frequency is 1 by RC. Okay, and at 0 frequency we have 1 gain, right? At 0 frequency, put 0 here, the gain will be 1. Okay, and what you are doing, exactly like the same analysis that we did previously. What you are doing here is that this is your input, and input, what is input? Input is square wave, right? And the square wave has DC, F naught, 3 F naught, 5 F naught, all these components, right? And you will have some output. Now what is given? Given is that your T is very lesser than RC, right? So your F will be very greater than 1 by RC. So DC is 0, like this is 0. Here we have DC. Here we have DC, this one. Apart from all the components, F node, 3 F node, 5 F node, all these components, F node, 3 F node, 5 F node, all these components will be greater than 1 by RC. So if this is the filter, here we have 1 by RC. In these region we will have F node, 3 F node, 5 F node. So except DC, all the frequency component will go through high attenuation. Right? Except DC, all the components will go through high attenuation. So the filter will mainly pass only DC, right? The filter will mainly pass only DC. So your output will be the average value of input only. So what is your output? That will be 5 volt. But the rest of the frequency component will be passed, but a little bit of attenuation, right? Rest of the frequency component will be passed, but with more attenuation. Sorry, the rest of the component will be passed, right? They will be passed with much more attenuation, but they will be passed, right? So we will not have a complete 5 volt DC. We will have some attenuation. So your waveform will go like, we will have some attenuation. These attenuation we have. This is the attenuation we will have, but the average value will be 5 volt. It will be nearly 5 volt. It will go 5.0001 and 4.99999. That's how it will go. But this value will be, this complete value will be this here. This value will be 5 volt. Okay, this is your V naught T. This, that's how you can also analyze the circuit. What did you see here is that all the frequency components were very much greater than 1 by RC. All the frequency components were very much greater than 1 by RC. So the filter would pass only the DC component with zero attenuation. Only the DC component with zero attenuation. Rest of the component F0, 3, F0, 5, F0 will also pass, but with very high attenuation. If they are passing with very high attenuation, they will have a very small impact in the output. So they will distort the output waveform. They will not give you a simple DC of 5 volt, but there will be some attenuation, but the average value will be around 5 volt only. So that's how also you can analyze the circuit with the concept of filter. Okay, so you can see it as a low pass filter as well, and previously we saw it with the intuitions, like how you should go, the current is getting increased, the current is getting decreased. Okay, by this analysis we saw it, and in the previous analysis we saw this waveform. Okay, so I hope every doubt that you had regarding this point is clear. Okay, so they ask these kind of questions in interview. Now they can replace, now they can change the uh, what do we say, change the position of R and C. They can put C here and R here, and then tell you to do the waveform. We will see it in next video. Okay, okay, thank you. Hello everyone, now we'll see this circuit. Here the position of R and C are interchanged. You have to draw the waveform of output V0 for two condition. T is very greater than RC and T is very less than RC. So we will move a bit faster in this one because we have already seen the concepts. Okay, so the first condition is T is very greater than RC. So we have enough time. It means complete charging and discharging, right? Please watch the previous video first, then only watch this one. Okay, so complete charging and discharging. Okay, so for 0 to T by 2, what is happening? Your Vin equals to 10 volt. This is here 10 volt, this is capacitor C, and this is R. Okay, this is 10 volt and this is V naught. Now what happens is that this capacitor charges. If capacitor charges, that means your output goes low. Why so? Like this is VC, your output is V naught is V in minus VC, right? If VC is getting charged, the output is going low, right? So first let us draw the waveform of VC here. So here the VC is, this is VC T. VC is getting charged from 0 to 10 volt. So this is charged from 0 to 10 volt. Okay, so if it charged from 0 to 10 volt, your output, initially the capacitor is shorted, so your output is 10 volt, but slowly the capacitor is getting charged, so your output will go down, or from 10 to it will go to 0. Okay, so this is the output waveform. This was VC. Okay, the capacitor is getting charged, in this direction from left to right. Okay, so now for T by 2 to T time. Your VC value is 10 volt. Your V in is 0 volt. So this V in is 0 and the capacitor was getting charge in this direction, right? If we had V in here, then it was getting charge in this direction. So we will have 10 volt in this direction, right? And here we will have R. This is V0. Your capacitor was getting charge in this direction. So it was charged to 10 volt. Now this is 0. So here we will have, in this direction we will have 10 volt and here we will have V0. So now what happens is the capacitor discharges. Capacitor discharges. So your VC and V0 will be equal this time. Actually it will be exact opposite, not equal. So just talking about V0. Talking about V0 from this was for 0 to T by 2. So first we had 10 voltage, then to 0. Then at T by 2, we will having 0 and minus 10. So at T by 2 we are having minus 10 voltage. So at T by 2 we are having minus 10. Okay. Now we are having minus 10. Now the capacitor is getting discharged. So capacitor is getting discharged. So this 10 volt is going down. From 10 volt we will go to 9 volt. So your value will be minus 9 volt here. So from 10 volt we are going down, down, down and we will go to 0. Okay. From 10 volt we are going to 0. Do you get it? When Vin is shorted, the V0 goes to minus 10 and now the capacitor is getting discharged. So if the capacitor is getting discharged, so the voltage across the capacitor is going low from 10 to 9, 9 to 8. Then from minus 10 to we are going towards 0. So eventually the capacitor will completely be discharged and it will go to 0. So this cycle goes on from 10 to 0, from minus 10 to 0. The same cycle goes on. Same cycle goes on. Now you can draw the output waveform by your own. Let me draw it here only. Okay. So again from here 10 to 0, from 10 to 0, then from minus 10 to again 0. So like this we are having the voltage waveform. Okay, do you get it? Now we will see the second condition. Okay, the second condition is also you can see this analysis by the concept of body plot or the frequency response. Okay, let's see the analysis by the concept of body plot. So what is happening is here is this is your CR, C, this is V in, this is V output. Let us call it method 2. So your V naught S upon V in S is SRC upon SRC plus 1, right? You can write it. Okay, so this is what? This is high pass filter, right? High pass filter. So the response will be something like this. The V naught as, this is V naught as, and this is V naught. We have a 0 at 0, so initially it will rise. It will rise like this, and then at 1 by RC, this is at 1 by RC, we have a pole. So first it rises, then it saturates. Rises, then first 20 dB per decade, plus 20 dB per decade, then minus 20 dB per decade, means 0 dB per decade. So it will be a constant. So this is 3 dB frequency and this is gain 1. Okay, this is gain 1 and this is 3 dB frequency. Okay, so what is given, like here we have a input that has frequency component of 0, f0, 3 f0 and so on, and then we will have some output. Okay, And what is given? Given is that T is very greater than RC. So your frequency is very less than 1 by RC. So all these components 0, F naught, 3 F naught, all these components are very less than 1 by RC. So if all these components are very less than 1 by RC, so all these components will lie here, right? All these components will lie here. So all components go through high attenuation, right? So your V0 will almost be equals to 0 volt. Okay, do you understand it? Like this is the circuit. At steady state, what happens? The IC average will be, at steady state, the IC average will be 0. So this will be open circuit. So your V0 average will come to 0 only. Or by this waveform, you can also see it suddenly comes down to, all of a sudden it comes down to 0 very early, right? From 10 to 0, it comes down very early. Then from minus 10 to 0, it comes down very early. Like we have drawn it like this, from 10 to 0, it comes down very early. If we have very large time, if we have very large time window, then it will come down very early. From minus 10 to 0, it will come down very early. So it comes down very early from 10 to 0. So most of the time it remains at 0 only. Okay, you understand it? So it is 0 only from 10 to 0 very quickly, from minus 10 to 0 very quickly. So we are having some impulse from 0 to 10, then from 0 to minus 10 we are having some impulses. But if you forget about impulses, then the output will almost be 0 every time, because the capacitor will be charged to 10 volt very quickly. The capacitor is charged to 10 volt very quickly, so output will be 0 only. Okay, or you can say the IC average at steady state will be 0 volt. So this will be the condition R V naught, and this is here V in. Okay, so whatever the value is V in, so here the current will be, IR average will also be 0. So your V naught average at steady state will be 0 volt. This is 0 ampere. Okay, and your VC average at steady state will be VI average minus V naught average. What is VI average? That is equals to 5 volt minus 0 volt. So it will be equals to 5 volt only. Okay, so all the aspects are clear now. Now the second condition, tau is very less than RC. So we have less time window. So here incomplete charging and discharging. Charging and discharging. Okay, so in this condition I will directly draw the output waveform now. From 10 to, it will try to go down, but it can go down to only 8 volts. Okay, I shouldn't draw it directly, because many of you will not be able to understand them. This is R, this is here 10 volt, this is C, and this is V naught. Now the capacitor is getting charged. The capacitor is getting charged with 10 by R current, right? 10 by R current, charging speed. This is charging. We are talking about V naught. So capacitor is getting charged. Let us assume it is charged to 2 volt. Now it is charged to 2 volt. Now at T equals to T by 2 plus, your V in is 0 volt and your VC is plus 2 volt. So this will be the condition. Here we have plus 2 volt and this is R. Discharging speed is discharging speed is 2 by R now, right? So if here we have a gain of, here the capacitor is getting 2 volt gain, 2 volt. Here the capacitor, here we have a gain of 2 volt in the capacitor. So what will be the loss here? Lesser than 2 volt, right? Because the speed of discharging is less. Here the speed of charging was more. Here the speed of charging is less. Here the speed of discharging is less. So the loss will be lesser as well, right? So V naught will go something like this. We are going from 10 to 8 volt, 10 volt to 8 volt. Then we will have minus 2 volt here. I should draw it from here. This is the, at t equals to 0, t equals to t by 2 plus, we will have minus 2 volt here. Then it will discharge from minus 2 to, let us assume it discharges to minus 1 volt. So from minus 2 to it discharges to minus 1 volt. This is t and this is t by 2. Now at t equals to, this is what, V naught t. At t equals to t plus, what do we have? The Vin equals to 10 volt. Now the capacitor is charged to 1 volt. Vc is at 1 volt. Now Vc is at 1 volt. So Vc is at 1 volt. Now the capacitor is charged to 1 volt, right? This discharges and discharges until the capacitor is having 1 volt. So the capacitor is charged to 1 volt. So what is the circuit now? This is C R. This is charged to 1 volt here, and here we have 10 volt, and this is your V output. So now drawing the waveform, from 10 to 8 is good, it goes. Then from minus 2 to minus 1 it goes. Now it will start from 9 volt, right? It will start from 9 volt. So from 9 volt it will go down. But here we went from 10 to 8 volt. So here we had a decrease of 2 volts. So now the speed of discharging is 9 by R. Sorry, charging is 9 by R. Capacitor charging speed. Capacitor charging speed. So now the speed of capacitor charging is decreased, right? Here we had 10 by R speed. Here we had 2 by R. Now we are having 9 by R. We went down for 2 volts. Here we went down for 2 volts. Now we can't go down for 2 volts. We can go down till 1.5 volt. From 9 to 7.5 voltage it can go down. 9 to 7.5. So here we had a decrease of 1.5 volt. Here we had a decrease of 2 volt. So from 9 to 7.5 we have reached. So now the Vc is 2.5 volt, right? Here we have 10, here we have 7.5. If we, here we have 10, here we have 10, here we have 7.5. So the Vc is now 2.5 volt. So now at t equals to 3t by 2 plus, your Vin is 10 volt, your Vc is plus 2.5 volt. So now the circuit is something like this. This is the capacitor C. This is resistor R. This is 2.5 volt, right? 2.5 volt. 2.5 volt. And this is V naught. Now the speed of discharging is 2.5 by R. So now the speed of discharging is getting increased, and the capacitor discharges more than the previous cycle. More than the previous cycle. Okay. Volt, 10 to 8 volt, then minus 2 volt to minus 1 volt from 9 to from this is 9 volt, from 9 volt to 7.5 volt. Okay, then from minus 2.5, from here we are starting now, from minus 2.5. Now it went down for 1 volt, so it will go down from more than 1 volt. Let us assume it goes down to it went down for 1 volt, right? 1 volt. Let us assume it goes down for 1.3 volt. So from minus 2.3 it will reach to minus 1.2. Okay, so this value will be minus 1.2 volt. Now if this is minus 1.2 volt, then again the capacitor will be having 1.2 voltage, then the output voltage will start from 8.8 volt. Okay, then the output will start from 8.8 volt and it will go down, and the same cycle goes on. Okay, so now the same cycle goes on 8.8, from 8.8 voltage. This will be 8.8 voltage. Okay, so this same cycle goes on. Okay, so steady state will be reached. Charging speed equals to discharging speed. That will be steady state. Steady state will be reached when charging speed equals to discharging speed. So at what point it will be equal? At 5 by R, right? Because the discharging speed is getting increased. 2.5 by R. Now we had 2.5 by R, previously we had 2 by R, and discharging speed is getting decreased. 10 by R, 9 by R. Okay, so here we had 2.5 by R. So this is charging and this is discharging. Okay, so the steady state of so the VC average at steady state, it would be 5 volt. Then only we will have 5 by R current, right? Like this is your capacitor and this is resistor. Here we have 10 volt, and if we have 5 volt here we have V in actually. So if V in is 10, then the speed of charging is 5 by R. If V in is 0, then the speed of discharging is 5 by R. Right? If V in is 10, the speed of charging will be 10 minus 5 by R. So it would be 5 by R. And if V in is 0, it would be the speed of discharging would be 5 by R. So VC average at steady state will be 5 by R. So your V naught average at steady state will be 5 minus 5. So it will be 0 volt. Okay. So that's about the second circuit. And also talking about IC average at steady state or IR average at steady state. This will also be 0 ampere. Or you can see it by the concept of that current waveform that we drew initially. Initially we have drawn a current waveform, right? So if Vin is 10, then the current will be 5 by R in positive direction. If Vin is 0, the current will be minus 5 by R. So first we had 5 by R current, then minus 5 by R current, then 5 by R, then minus 5 by R. So what is the average value? That is 0. So that analysis we have also seen. Now you can do the analysis with the concept of Bode plot. So this is method 2. So this is our RC circuit. Okay, and this is our low pass filter with this 3 dB cut off frequency equals to 1 by RC. Okay, so here we have these components 0, F0, 3 F0, all these frequency components we have. And what is given? Given is T is very lesser than 1 by RC. So your F will be very greater than 1 by RC. T is very less than RC. So F will be very greater than 1 by RC. So your F0, 3 F0, 5 F0, all of them will be very greater than 1 by RC. Now this DC value will be here. Here we will have DC. So only DC will be blocked. Only DC will be blocked. Right? So only DC will be blocked. So here the DC value. What is the DC value? DC value of input. DC value of input. DC value of input is 5 volt. So that will be blocked. So your output will be V input minus 5 volt. You get it? Your DC will be blocked. These F0, F0, 3, F0, 5, F0 will come here. And here we will have DC. So this will be blocked. Only these components F0, 5, F3, F0, 5, F0 will pass. So your output will be input voltage minus 5 volt. So what will be the output? So output will be something like this. Steady state output will be something like this. Yeah. So V naught T will be at steady state. It will be 10 minus 5. That means 5 volt. 0 minus 5. That means it will be minus 5 plus 5 minus 5 plus 5 and minus 5. So this will be the output waveform. Okay, output waveform as steady state. At steady state. Okay, so what is the average value of output waveform at steady state? V naught average at steady state, that is equals to 0 volt. And also we derived it previously. What is the average value of output at steady state? That is equals to 0 volt. And here also you can see the output voltage at steady state is 0 volt. So this analysis we have also done. So I hope you have understood all the aspects regarding these two questions, these two RC circuits. So I will give a small summary now. Okay, so we will see it in next video. So summarizing the video, this was our first circuit, first RC circuit. Okay, this was the input waveform 10 volt and 0 volt. This was input. This was our low pass RC circuit. And there is one more thing, like I won't be able to provide the lecture notes for this this previous analysis, because the notes got deleted by mistake. Like I am really sorry for that, but the notes got deleted. I will provide the handwritten notes, but the lecture notes won't be provided for this one. Okay, so this is RC low pass filter. There was two kind of output. Like it's a really bad feeling for me as well that the notes got deleted. Like it was very nice analysis. So I thought I would provide the notes, but those got deleted. So in this one, output was something like this. Okay, then this. Okay, and for this it was first update, then some value gain. So we have done all the analysis. We are just writing the summary now. Okay. So what was your V naught average at steady state? It was same as input average, that means 5 volt. What was your IC average at steady state? It was 0 ampere. What was your VR average at steady state? It was 0 volt. And what was your IR average at steady state? It was 0 ampere. Okay. And the second one, C and R. C and R. Here we had this input 10 0 10 0. Okay, 10 volt and 0 volt, and this is V naught. Okay, this was RC high pass filter. we had two output. Two kind of output we had. From here to here, and then from here. Okay, this was for T is very greater than RC. This is V naught T. Okay, and V naught T for this one, that was something like this. Okay, and the same cycle. So what was your V naught average at steady state? It was 0 volt. What was your VC average at steady state? It was same as input average, that was 5 volt. Your IC average at steady state and your IR average at steady state, both were equal, and that was equals to 0 ampere. So we have done the complete analysis by all the possible method. By body upload that we saw, by IC average method that we saw, then we simply saw intuitive analysis of voltage waveform. So all the method we have seen here. I hope you have understood the concept clearly. Okay, so these videos are very important for interview. Okay, thank you.